Hello everyone. In this video we are going to discuss practice exercise 1.5 from your very first chapter, that is vector algebra. Okay, so we will start with what is given to us. So very firstly we are going to write what is given. So we are given with the two vectors. Very firstly we have the vector E, which is equals to 3ay plus 4az, and then we have another vector, that is vector F, which is 4ax minus 10ay plus 5az. Okay, now here in this numerical, in the very first part, we have to find out what is the component of E along F. What is the component of your vector E along vector F? Okay, so whatever is that components of any of the vectors, it has been broken down into the two parts. So component of that vector. So very firstly, we will just review that one. So vector components or components of given vector is basically classified, or you have the two parts. Very firstly we have the scalar component, that is also said to be what? A scalar projection of one vector onto another vector. So this is what we have, scalar projection, and another part that we have is the vector projection. See, if it is given to you specifically in your numerical, that where we have to find out scalar projection, then go with the scalar projection. If it is specifically given, we have to find out vector projection, so then go with the vector projection. But here in this case we are not given with any of the specific component, whether we have to find out scalar component or whether we have to find out vector component. So I will suggest that you should go with this, that we should have to find out its vector projection. And this scalar projection, it is also said to be a parallel component of one vector onto another vector, and this vector projection, it is said to be a perpendicular component of one vector onto another vector. Say for now we have vector A, then perpendicular component of vector A onto vector B. So this is what? So scalar projection, that means we have to find out parallel component, or parallel component, that means we have to find out scalar projection, and perpendicular component is nothing but your vector projection, and vice versa. Okay, so these are the components of any of the given vectors. So here in this case we have to find out component of vector E onto vector F. So we are going to find out its vector projection. Okay, so we will begin with the part A of this same numerical. Okay, so in order to start with component, very first part of your this numerical, very firstly we are going to rewrite our vector E, since x component is missing over there. So after rewriting that one, we will have that 0x over here, which is not given over there. Then we have the 3ay, then we have the 4az. So this is your vector E, and another vector F is given to us. Now very firstly we are going to find out, in order to find out the component of vector E and along vector F, so very firstly we are going to find out the scalar projection of one vector onto another, or here in this case for this numerical we are going to say we are going to find out scalar projection of that vector E along vector F, and this is another name given to this one is also said to be, we are going to find out what? We are going to find out parallel component of your vector E along vector F. Okay, fine. So what is that scalar projection? How it is given? So scalar projection of one vector onto another vector. So here in this case your very first vector is what? Vector E. So we are going to write that one. So that is your vector E, and along vector F. So here in this case we are going to take its unit vector. So this is said to be the scalar projection of one vector onto another vector. Scalar projection of vector E along that vector F. So we have to write it in this form. So that will be your given vector having the dot product with respect to the unit vector of your this second vector. So now we will write that vector E. So what is vector E that we have? So vector E, we have that to be the 0ax plus 3ay plus 4az. So this is your vector E, and it have the dot product with respect to the unit vector of your another vector, that is vector F. So what is the unit vector for that vector F? So that is from the, you can recall the basic definition of unit vector. So what we have unit vector? So whatever is your unit vector is represented by this letter A, small a, and here in this case unit vector of your vector F, it will be what? Given vector F divided by its magnitude. So this is your unit vector along that F direction. Okay, so what is your given vector F that we have? So we have the vector F to be 4ax minus 10ay plus 5az divided by its magnitude. So what will be its magnitude? So that will be in the square root of this 4 square, then minus of 10 square plus this 5 square. So this is the magnitude of your vector F. Okay, now simplify that one. So very firstly we will go with the dot product component by component fashion. So 0 into this 4, so we will add that value to be 0, then plus this 3 into this minus 10, so that will be what now? So that will be minus of 30, then this 4 into this 5, so that will be what now? That will be plus of 20 divided by this square root. So if you simplify that square root, so you will find that to be the square root of 141, and again if you go for this further simplification, so you will find that value to be minus 10 divided by 11.87. You can have your calculations. Okay, and ultimately your final answer will be equals to what now? So that is equals to minus of 0.842. So this is what? This is your scalar projection of vector E along vector F. Scalar projection of vector E along vector F. Okay, so this is the very first part of the same example. That is your part A of the numerical. Now we will move on to the second part, that is we have to find out what is its vector projection. Okay, so vector projection will be given by means of this. So vector projection of vector E along vector F, it will be given by means of the scalar projection of scalar projection. See, this is for your understanding purpose. You need not have to write this in your exam or whatever. So it is what? Scalar projection of your one vector onto another vector. So scalar projection of vector E along vector F having the dot product with respect to the unit vector of your second vector. So here in this case we have the second vector to be vector F. So this is how you are going to write for that vector projection of one vector onto another vector. And this is also said to be what? It is said to be the parallel component, or you can say the parallel projection. of one vector onto another vector. Okay, so this is what we have for that second part of the numerical. Okay, now we have the value for the scalar projection of vector E along vector F, that is to be equals to what? Minus of 0.842. Then we will have its dot product with respect to the okay, let me represent it you how you are going to write it down. So that will be equals to what now? Scalar projection of one vector onto another vector, and then having its dot product with respect to the unit vector of your another vector, that is vector F here in this case. Okay, so we have this value over here, which is nothing but what? Vector E dot unit vector AF. Okay, so we have this value to be what? Minus 0.842, having the dot product with respect to your vector F. And what is that unit vector along that vector F? So that is already we have written 4ax minus 10ay plus 5az divided by its magnitude. So what is that magnitude? So that will be 4 square minus of 10 square plus of 5 square. Okay, now we will simplify that one. So meantime I am going to write it down. You can have your own calculations so that I can directly write down the values for that one. Okay, so we will put this term into the square bracket and we are going to simplify that one. So this minus 0.842, it will be as it is, and further simplification. So if you are going to further simplify that one, so you will have this final answer. Okay, so this is the answer for your very first part of the semi-numerical, that we have found out the component of one vector onto another vector. Now we will move on to the part B of the numerical. Now in part B of the numerical, we have to find out what is the unit vector that will be perpendicular to your both given two vectors, that is vector E and vector F. Now for here in this case, we are going to make use of the cross product. So from the basic definition of the cross product, what we have? So if we are given with the any two vectors, so here in this case we are given with vector E and vector F. So the cross product in between the two vectors will be given by the product of the magnitude in between them and sine of the theta, or you can say the angle in between these two vectors, having the normal vector which is perpendicular to the both vectors. So what is this thing? So say for now you are given with this vector E and we have another vector, that is vector F. So these two vectors, if they lie in the same plane, so there will be always a normal vector which will be perpendicular to these both vectors. So here in this case, that normal vector which is perpendicular to this plane is given by means of this AN. Now this normal vector, it can be in the positive direction as well as it can be in the negative direction. Since the direction of this normal vector is not specified over there, so we are going to denote it by using the plus and minus sign. Okay, so this is the concept of that normal vector for your given two vectors. Now we will move on to the numerical. So let's say this is to be the equation number 1. Now for a normal vector or for perpendicular vector, what we have? We will have that theta value which is equals to 90 degrees, and if that theta is equals to 90 degrees, so here in this case, whatever is this sine theta EF, it will reduce to what? It will reduce to 1. Since we have the sine 90 is equals to 1. Okay, so here in this case, your equation 1, it will reduce to what form? So equation 1, it can be rewrite like this one, that E cross F is equals to magnitude of vector E into magnitude of your vector F. Now we have this value to be 1 and this an cap over here. So this is, say for now, this is your equation number 2, and further if you are going to rewrite this equation number 2, so from that you will find the value of that normal vector to your both given two vectors, that is vector E and vector F, which will be equals to like this one. So we will have that value to be E cross F divided by magnitude of E into magnitude of this F. So this is what we have for our normal vector to your both two vectors, that is vector E and vector F. Now if you look out, so what we have to find out? So very firstly we have to find out what is this E cross F, and then we have to find out the product in between the magnitudes of that vector E and vector F. So we will move with that one. Now that E cross F will be written like what? So we are going to write that E cross F to be equals to this one, determinant of your this AX, AY and AZ. So what is the component along E? So for that E we have AX to be 0, then AY is equals to 3. You can see the given numerical, and for that component along Z direction is we have magnitude equals to 4. Now for that Y, so for that Y we have this to be, sorry, for that vector F, so for that vector F we have this to be 4, then minus 10, and then we have that value to be 5. So this completes your determinant. Now we are going to simplify that one. Okay, so if you are going to simplify that one, we have this AX very firstly, then AY, sorry, AX within the very first bracket. So we will have that to be the this 3 into 5. So this will be 15 minus this 4 into minus 10. So that will be minus 40. So minus minus value, it will get per plus. So this will be 40 plus AY. So AY. So simplify that one. So for that AY we will have this to be this 4 into 4. So that will be 16 minus this 0 into 5. So that will be 0 plus AZ. Okay. Okay. So for that AZ, we will have this to be 0 into 10. So this will be 0, and this 4 into 3. So that will be what now? Minus 10. Sorry, minus 12. Now, what is the value that we have for that E cross F? So that E cross F is equals to what? So that will be 55 AX cap plus 16 AY minus 12 AZ. Okay, so we have this for your E cross F. Then next, you can go with this equation, or you can say this to be a say for now A. Okay, so from A we have a normal vector an is equals to, it can be of, it can be in the any direction, so we are going to write this to be plus and minus. Then your E cross F, so we have the value for that E cross F to be what, 55 AX plus 16 AY minus 12 AZ divided by magnitude of your vector E. So magnitude of vector E will be what now? So that will be, you can refer to your given statement. So that will be 3 square plus 4 square. Then magnitude of vector F. So that will be what now? So that will be 4 square plus minus of 10 square plus 5 square. Okay. Now simplify this one to get the answer. So meantime I will write it for you. So if you simplify these two square roots, so we will have that value to be 59.37. Okay, and now you can have the division over here so that you can get the normal vector to your both given vectors, that is vector E and vector F. So that will be an, and that value to be, I am going to write it for you. Okay, so this is your final answer. That gives you the unit vector which is perpendicular to both your given two vectors, that is vector E and vector F. Okay, so with this we have finished your numerical 1.5 from your very first chapter. Okay, thank you.